All right, welcome to The Explainer. Today we're diving into a wild new concept that could completely flip the script on one of the most common appliances we all have, the air conditioner.
I mean, it sounds like something straight out of science fiction, doesn't it? But what if the very machines we use to cool down our homes could also be heating our cities, all while using just a fraction of the energy? A brand new design concept is aiming to do exactly that, so let's get into it. Okay, so before we get to the cool new tech, we've got to talk about the problem. And to really get why this new approach is so critical, we need to face the serious issues with the air conditioning technology that we all rely on today. Just look at that number, 25%. That is huge. Think about it, roughly a quarter of all the electricity used in our cities goes directly into powering our heating, ventilation, and air conditioning, our HVAC systems. That's a massive, massive energy footprint. And, the problem here is really twofold. First up, you've got the mechanical compressors inside our AC units. They are just total energy hogs. But then there's the other shoe to drop, the chemical refrigerants they rely on. These things, called HFCs, are unbelievably potent greenhouse gases, way, way more warming than CO2 if they ever leak out.
All right, so that's the dilemma. How do you possibly fix that? Well, the source material proposes this radical bio-inspired solution. It's called the Ionocaloric Pollen sleeve. Now, on the outside, it looks like a simple drop-in replacement for an AC unit, but what's happening on the inside, well, that's completely revolutionary. And here's what it promises to do. The three core pillars of this thing. First, it gets rid of that power-hungry compressor entirely. Gone. Second, it uses zero HFC refrigerants, which means its direct global warming potential is basically nothing. And as if that weren't enough, it's also designed to actively clean the city air as it runs. Okay, let's stop for a second. How on earth do you make something cold without a compressor? I mean, that's how AC has worked forever, right? Well, the answer lies in this really fascinating bit of physics called the ionocaloric effect. It's this really elegant cycle. And the best part? No moving parts. It all starts with a tiny little electric jolt. We're talking less than 1 volt, applied to this special salt gel. This current pushes ions into the gel, and that makes it melt. Now, think about ice melting in your drink. What does it do? It makes the drink colder, right? Same idea here. That phase change, from solid to liquid, naturally sucks up heat from the air. Then you just turn off the voltage. The gel resolidifies, and in the process, it releases all that heat it captured, but it releases it outside. It's a simple, silent, and super efficient way to move heat around. And when you put the two side by side, wow, the difference is just stark. You're replacing a noisy mechanical compressor with a silent, solid-state process. You're swapping out that high power draw for a tiny voltage, so low you could easily run it off a solar panel. And you're getting rid of dangerous greenhouse gases for simple, harmless salts. I mean, it's a fundamental upgrade in literally every single category. But believe it or not, that amazing cooling engine, that's only half the story. The other key piece of this puzzle is the device's outer shell, this incredible pollen sleeve that has two really, really important jobs. So to really get what this sleeve does, we need to quickly talk about something called passive radiative cooling. It sounds complicated, but the idea is actually pretty simple. It's a natural phenomenon where certain materials can shoot out heat as radiation at a very specific wavelength. And this wavelength is special because it passes right through our atmosphere and out into the freezing cold of deep space. It's like having a magic window that just beams heat directly into the universe. And this sleeve puts that exact principle to work. It's coated in processed pollen shells, which turn out to be fantastic at radiating heat away. But that's not all. The natural, porous structure of these shells also makes them a perfect filter. They can actually trap those tiny, harmful pollutants like PM2.5 and microplastics. The whole thing is built onto a smart honeycomb frame that helps guide the air through the system with almost no effort. And the design has one more clever trick up its sleeve. There's a super thin film of gold flakes built right into the device. As the system runs, tiny changes in pressure cause this film to subtly shift its color. What does that give you? A simple, visual, real-time diagnostic. It's like a built-in health check for the system that doesn't need any complex electronics at all. Now look, a concept like this is amazing on paper, but it's only useful if it can actually work out in the real world, right? Well, the design includes a really rigorous plan to make sure this thing moves from being just a lab experiment to a practical, reliable piece of engineering.
Yeah,
This isn't just wishful thinking. The project has these incredibly specific, very tough performance targets it has to meet. They call them fail-fast gates. It must achieve at least a 25% energy saving. It must remove at least 40% of that nasty particulate matter from the air. And its global warming potential has to be effectively zero. If it can't hit these non-negotiable targets, the design is considered a failure, plain and simple. And they've got a really clear path to get there. It all starts small with a 1 kilowatt model on a lab bench. If that works, it graduates to a dust chamber to test its durability. And then the final boss, a full-scale 7 kilowatt unit, gets put on a real rooftop, where it'll run head-to-head against a normal AC system for an entire year. And here's something that's just so crucial for making this work in the real world. It's designed to be modular. The outer pollen sleeve and the inner cooling core are two separate pieces. So what does that mean? Well, when that filter sleeve inevitably gets clogged up with city grime, a technician can just pop it off and swap in a new one. Super cheap. They don't have to touch the expensive cooling engine inside at all. It's just a smart, practical design. So let's just zoom out for a minute, because this really builds into something much, much bigger than just a better air conditioner. If you start to imagine this technology being used at scale, it could fundamentally change the way our cities actually work. The source material paints this absolutely incredible picture of our rooftops becoming part of a living thermal metabolism. Just think about that. Entire city districts where the buildings are actively managing heat, running on clean energy, and even providing an immune-like function for the whole city by constantly filtering out pollutants. They could even tell us when they're not working right. And this all leads us to one final, really provocative thought. We tend to think of our buildings as these static, lifeless objects. But with technology like this, that combines cooling and cleaning and even sensing, it really makes you wonder, could our buildings soon learn to breathe? And in doing so, help create a healthier world for all of us?